Okay, we've talked about troubleshooting a no start, how you find a misfire at idle. In a few minutes I'll show you how to test some of these sensors using a DVOM. But the one thing we haven't done is to do an EEC test. Now anytime you have a drivability concern, a check engine light, even a no start, it's a good idea to do an EEC test first. It may not tell you what's wrong, but it might lead you in the right direction. Now before I use my new code reader that has the nice display on it, I want to show you what the technicians used back in the mid-80s. And here it is, the infamous star tester. This was the first generation code reader from back in the mid-80s. This one's pretty much worn out. The LCD display is long since broken. But this actually was an upgraded version of the star tester because it had this little LED light on it. Even though the LCD display is broken, you can still read codes with this by counting the flashes of the LED light. So what we'll do a key on engine off test on this car just to show you how this star tester can be used by reading the LED light. We'll plug the test cable into the self-test connector on the car. Remember, it's two connections. You have this bigger hard shell and this single wire here. Now I'll go in there and turn the key on. Now I'll push this latch button down and we'll watch the LED. It's off now. When I push the button down, the LED will come on. Okay, I don't know if you can see it, but the light should start flashing now. There you go. 1, 2, 3, 1. That's a code 31. Let's see what else. 1, 2, 3, 4, 5, 6, 7, 8. 1. That's an 81 code. Now the LCD display would be displaying that if it was working. And this will go through some more codes. These are hard faults. Now the 31 code I can tell you is the EGR code, and the reason I'm getting that as a hard fault because I don't have EGR hooked up to this. 81 is one of the thermactor pump solenoids. Again, it's not hooked up, so I'm getting a code for it. Eventually it will display all of those codes and then repeat them. After it repeats the codes, there'll be a pause and you'll get a single blink. That's the separator code. Then you'll start getting the memory codes. And this will go on for a little while, so we'll just unlatch the button, and I just wanted to show you how this star tester could be used by counting the blinks. And we'll just unlatch that now. Okay, I have my new code reader hooked up now. It's the cable is hooked to the self-test connector. Remember, there's two connections. You have the larger hard shell and then that smaller single wire. And then we'll turn the code reader on and watch to see what kind of display I get. It may be a little difficult to see in the video, but I have a display here. It's telling me to make sure my self-test connector is hooked up, which it is, and then to push the little button on the right side here. Then it asks for what tests I want, and the options are key on engine off, timing check, key on engine run. I believe if I scroll this down I'll actually get a couple more options, but what we want is the key on engine off test. So we'll push that button again, and then it says to start the engine and warm it up. Now I'm not going to do that, but you do want to have a warm motor typically when you do this test. If it was the middle of winter, your coolant temperature would be so low that the test would evaluate that as a, say, ECT out of range, and you would get a code for it. It's the middle of summer here, so I don't think I'll get a false code with that. So I'll go ahead and click it again. Then it tells me to turn the ignition on, so let me reach in here and turn the key on. And then I'll push the button again. And you'll probably hear some clicks and pops. The fuel pump comes on. It's activating a few of the solenoids here, and I start getting some codes, and these are hard fault codes. The first one I get is a 31. Sure, 31 is the EGR system, just like I got on the star tester. I don't have the EGR hooked up, so I'm getting a open circuit code for that. Push the button again, I got an 81. That's one of the themactor pump solenoids. Again, I don't have that hooked up. 82, that's the other themactor pump solenoid. I think the acronyms are TAD and TAB for those two solenoids. 85, that's the canister purge solenoid. Again, I don't have that hooked up. And 84, and that's the EVR. That's the vacuum regulator that operates the EGR. Once again, that system is not hooked up on this project, so I'm getting a hard fault for it. Click the button again, and this is memory codes. Well, the memory code is an 11. 11 is a passcode. But believe me, this car would have some memory codes. The reason it doesn't was earlier when I used the star tester, you might remember, I unclicked the latch button in the middle of doing the test. When you do that, that clears the memory codes. If I drove this car down the road, came back, most likely I would have the 31 code in memory. I might have the, say, 84 as well, because during the road test it would have turned on the EGR, and of course, because they're not there, I will get a code for it. Another test I can do with this is the key on engine run test. What I would do on a warm motor, I would just use, follow the instructions. It would tell me to start the engine, turn the steering wheel, hit the brake pedal. It would ask me to rev the engine up one time. And what it's doing, it's reading oxygen sensor, it's reading throttle position sensor. When you kick the throttle, it's looking for a voltage change. If it was a mass air equipped car, it would be looking at voltage changes on the mass air system to make sure that was operating as the engine RPM goes up and down. And so, you have several tests here. They're all good to use if you have a drivability problem. It may lead you in the right direction of possible concern. There's a couple other tests here. You can do the ignition timing test. What it will do when you go into that mode, you can check base timing without pulling that spout shorting bar. And you have about a minute, I think, to check that. So that's kind of nice. If you have one, maybe the shorting bar is a little bit hard to get to, you can do that test. Some of these cars will have a cylinder balance test, not all of them, but some of them will have a test where it actually starts cutting injectors off and looks for a certain RPM drop. If you had an engine that was missing or was not contributing, say you had maybe a weak cylinder, it would detect that and you would get a code for the cylinder that's causing the problem. So I think the next thing we'll do, we'll go over here and we'll start checking some of these sensors using a DVOM. I have the digital voltometer in the engine bay here close to the throttle position sensor. That's the first sensor I want to test. And the first test that I want to make is to verify that the signal return has a complete circuit in the sensor. The way I'll do that is I put the meter on the ohm scale. I have one probe wire hooked to battery ground over there, and then I'll use the other probe wire to back probe the signal return wire on the hard shell. I pulled back the little weather connection here to make it a little bit easier to back probe these wires, and the signal return happens to be a black wire on this one. You have to look at your color codes to know if that is the correct color. This wire, of course, eventually goes to pin 46, which is the signal return connection on the processor. And I should get a complete circuit. I should have a very low ohmic reading here. So let's give it a try. There you go, 1.4 ohms. Less than 2 ohms. That's exactly what I want to see. That's a complete circuit. So I know that wire is going to pin 46 and it's also grounded internally in the processor, which is what I want. Next, I change my scale to volts and I turn the key on. Now I want to check the reference voltage. On this one, it happens to be the orange wire. I'll back probe that and see what I get. Okay, we have 4.91 volts, and that's what we want. We want very close to 5 volts, give or take a tenth of a volt or so. That's a good reading. So reference voltage is correct. And the reference voltage is pin 26 of the processor. So we know that's a complete circuit. Now I want to check the signal wire. That's the wire that's going to pin 47 of the processor. That's the voltage that the processor will read as the position of the throttle. So let's see what that is with a closed throttle. The wire is green on this one, and I'm getting a reading of 1.01 volt. That's perfect. You want it close to 1 volt, give or take a tenth of a volt. And 1.016, that's perfect for a closed throttle. Now what I want to do is to exercise the throttle and make sure that the voltage changes with the throttle blade angle change. You may not be able to see the display very well, but what I'm going to do is to move the throttle from the idle position all the way to full throttle. And I should see a steady climb in the voltage. If I suddenly see 5 volts or if I suddenly see 0 volts, then there's an open circuit in that throttle position sensor, and most likely that would have to be replaced. I want to see a smooth transition from this 1 volt position up to approximately 4.5 volts at wide open throttle. Let's see what we have. All right, slowly move it. I got 1.4, 1.8, 2 volts, 2.8 rather, 3.1, 3.5, and I think I have it in the wide open throttle position, and it's 4.50 at wide open throttle. And I saw a steady climb of the voltage. That's very good. Go back to the stop idle position, and I'm back at 1.02 volts. That's perfect. Let's go over to the chalkboard and evaluate what the readings we got. The throttle position sensor, which is a 3-wire sensor, is what is called a potentiometer. One wire is going to 5 volt to the reference voltage, one is going to ground, signal return, and then the signal wire is actually a wiper that's going across a resistor. Now you remember at closed throttle we had 1 volt, so in other words the wiper is closer to the ground side. As I moved the throttle blade to wide open throttle, I got 4.5 volts, so it went, the wiper went closer to the 5 volt side. So, and we had good readings here. You should never see 0 voltage, and you should never see 5 volts on the signal wire. If you ever see 5 volts, most likely the signal return wire is broken or open circuit, or the signal wire is shorted to the reference voltage wire. If you ever get a 0 voltage reading, most likely the reference voltage wire is broken or has an open circuit, or the signal wire itself is simply broken and you're getting a 0 voltage reading. Now there's other potentiometers on the engine. The EVP, that white sensor that's on top of the EGR valve, that's a potentiometer too, and it basically has the same type of setup. You have a reference voltage, signal return, and the signal wire. And typically with the EGR closed, the signal voltage will be something like 0.4 volts, and with the EGR wide open you would have something like 3 volts. If you had, say with the engine cut off, you had a signal voltage of maybe 0.8 or something like that, most likely you have an EGR that's stuck off its seat. And you may also have a symptom of real bad idle, because of course now the exhaust is going into the intake at idle. That's definitely going to cause a bad idle problem. Okay, now let's go back to the car and we'll check the ECT sensor and test that. I still have the DVOM hooked up. One test lead is hooked to the battery ground like it was before. I'm going to turn the key on, then I'll use the other test lead and back probe the signal wire on the ECT. Remember, on this engine the ECT is mounted on the left hand side of the intake. So I'll back probe that and see what kind of voltage reading I get. 2, 1. Okay, I have a reading of 2.38 volts, and that's telling me that the temperature is relatively low. The way the voltage reading is on an ECT is it's inversely proportional to the temperature. So in other words, if the temperature is low, the voltage is high. As the temperature goes up, the voltage goes down. Now a reading of 3 volts would tell me that the coolant temperature is about 70 degrees. Well, I have a lower reading than that. Well, this engine was run about a half an hour ago, so the coolant temperature is probably just a little bit more than 100 degrees. That's why I'm getting a 2.3 volt reading. Now, if I start this engine up and warm it up until the fan comes on, remember the fan comes on at 200 degrees, then I should have a reading of about 0.52 volts. And again, inversely proportional. As the temperature goes up, the voltage would go down. So in a little bit, I'll start the engine up until the fan comes on, and we'll take a reading then. Take a look at the reading at that time. Now let's take a reading of the ACT. It's right here close by. And we'll give that a look. Okay, I'm getting a reading of about the same thing, 2.38. Well, that makes sense because the air temperature is about the same as the coolant temperature because it's been sitting here for a while. Now, when I warm the engine up, the coolant temperature will rise much quicker than the air temperature, and most likely the air temperature will always be slightly cooler. Even though you're getting some rise in temperature from engine heat coming up into the intake, obviously air coming through the air filter and everything will always be slightly cooler, so you should always get a slightly cooler reading on the ACT, or the air temperature sensor. Okay, I've cut the engine off, but I've turned the key back on, and of course you can still hear the fans running. I have a ECT voltage of 0.59. That's about 190 degrees. Now I want to check the ACT, the air temperature voltage, and see how much different that is from the water temperature, the coolant temperature. Okay, with the ACT voltage of 2 volts, that translates into about 130, 140 degrees. So obviously it is picking up some engine heat into the intake, but of course the temperature is much lower than the coolant temperature, and that certainly makes sense. Over here at the chalkboard, I want to explain what we're looking at when we take a reading of the ECT or the ACT. Remember, these sensors have a variable resistor inside, and the resistance changes with the temperature. Remember, it's inversely proportional, so as the temperature goes up, the resistance goes down, which makes the voltage go down. You have 2 wires going to the sensors. One's a signal return, just like with the throttle position sensor, and the other one is the signal wire. And when it gets into the processor, it's going through a pull-up resistor that's going to reference voltage. So with the wire unplugged, the signal wire should be pretty close to 5 volts. When you plug it in, however, now it has to go through that resistor. And the hotter it gets, the less resistance you have, forcing that signal to go further to the ground side, or in other words, making the voltage go down. Now, what if I probed that signal wire and I got 0 volts? Well, there's a chance that the wire going back to the processor, of course, has an open circuit. It's also possible that the sensor itself is shorted on the inside, causing me to have a 0 reading. What if it's the other way? Say I have a warmed up motor and I'm getting 4 volts or more than 4 volts. Well, you could still have an open circuit in the sensor, still a bad sensor. But before I condemned the sensor, I would check the signal return with the ohm meter, just like we did with the throttle position sensor, just to make sure that wire is going all the way to the processor and I have a good ground signal there. If I do and still have a high voltage reading, most likely the sensor is bad. And you would read ECT and ACT exactly the same way. Over here I've made a little chart of some landmark temperatures and the corresponding voltage. Go down here at the bottom, you see 70 degrees Fahrenheit now. You should have about 3 volts on that signal wire. At 175 degrees Fahrenheit, you should have a 0.8 volt. At 200 degrees Fahrenheit, you should be about a half a volt, 0.52 or thereabouts. If you're starting to overheat, you get up here about 230 degrees, then your voltage will be a 0.36 or lower. You start seeing a 0.30, something like that, you're definitely getting into no man's land. You're getting a hot motor, and you will probably start seeing some antifreeze ooze out from that radiator cap. While we're at the chalkboard, I want to discuss the next sensor that we are interested in, and that's the oxygen sensor. One of the things that's unique about the oxygen sensor is that it makes its own voltage. So let's talk about that for a minute. Oxygen sensors produce voltages between 0 volt and 1 volt. And you read that voltage by the closer to 0 volts you are, the leaner the mixture. The closer to 1 volt you have a very rich mixture. They are calibrated in such a way that at the midway point, or 0.5 volts, a half a volt, that should be giving you the perfect, what the engineers feel is the ideal air-fuel ratio, which is 14.7 to 1. That's considered stoichiometry. And a stoichiometric signal of a half a volt is telling you that the engine is at its peak efficiency when it comes to air-fuel ratio. So when you're looking at an oxygen sensor signal while the engine is running, it should be pretty close to a half a volt. When it's in closed loop, understand, in closed loop, that's when it's actually reading the oxygen sensor. On a cold motor, it's not doing that. At wide open throttle, it typically is not doing that. It's doing it more at idle and at cruise. Now, rarely will you see it stuck right at a half a volt. It actually will dither one way or the other. The processor will make slight adjustments to the shot rate of the injector, and what you will see is a swing. It'll go a little bit below a half a volt, and it'll go a little bit above a half a volt. At idle, you may see the swings about every second. When you bring the RPM up, you may see the swings several times a second. But it always should be, the average should be pretty close to a half a volt. Okay, let's go back over to the car. I'm going to start the engine up, warm it up, and I have a test lead hooked to the right-hand oxygen sensor so we can read the voltage while the engine is running. Okay, the engine's been running a little while, and it should be in closed loop by now, but what I'm seeing is a rich reading there. It's 1 volt, and it's staying steady at 1 volt at idle. But let me bring the RPM up about 2,000–3,000 RPM and see if it will go into feedback then. Let's give it a try. Okay, with the RPM raised, you did see it go into feedback. You saw it go below a half a volt and above a half a volt, about every second or so. You did see it a little bit to the rich side in most cases during the swings, but you did see it go below a half a volt. So it is going into feedback with the RPM up, without any real problem. Okay, well, what did we learn? Well, I found that the oxygen sensor does work, and when I brought the RPM up, it did go into closed loop, and I saw the oxygen sensor switch back and forth, so I know it's operating okay. The one concern I had was at idle, it looks like it just stuck in the rich position and it wouldn't switch. Well, what I interpret that as is this engine setup is likely a little bit beyond the threshold of what a speed density system can operate under in an efficient way. I think what happens is it tries to go into closed loop at idle. Maybe the RPM starts fluctuating a whole lot. It looks at its internal software, it says, wait a minute, something is, kind of beyond the strategy in which this thing is going to work very well. It goes back into open loop, and then the idle kind of smooths out. So what I find though, the thing runs fine on the road, and when you put it in gear, it idles relatively smooth. It has crisp throttle response. So I'll definitely be able to drive the car this way. But it does tell me that this particular project would most likely be better served if I changed it over to mass air. Now, what if I wasn't getting a reading? What if the voltage stayed at 0 the whole time? Well, I may have a bad oxygen sensor, and in that case, I'd want to check the one on the other side. If that one's switching, then most likely I just simply have a bad oxygen sensor. If neither one of them was working, I was getting 0 volts from both of them, well, it could be that the ground, remember that orange wire going to the back of the intake, that may be off or corroded. So that needs to be checked. But if all of that checks out okay and I still have 0 volts, I likely just simply have a bad oxygen sensor. Either that or the thing is running extremely lean. And if so, you would have a terrible drivability concern at that time. All right, what if it was the other way around? What if I got a constant high reading? I was getting 1 volt, whether I revved it up or what? Well, of course, if it was blowing black smoke out the back, well, most likely you got something wrong. You got a pressure regulator broken, or maybe the diaphragm is ruptured and fuel is actually, raw fuel is going through the vacuum line going right into the intake, so you need to check that. But if the fuel pressure checks out all right, and it seems to be kind of running okay, but it's showing very rich, you may have something out of calibration. Maybe you have the wrong fuel injectors in the car, or if you have a mass air sensor equipped car, you may have a mass air sensor that's the wrong one. It's not calibrated for the injectors that you have, so that needs to be checked out. But all in all, what I wanted to show here is that you can check the oxygen sensor, and you do want to see it switch at least when you bring the RPM up. And one other thing, if you have a way to check the reading of the sensor when you're going down the road, you should see at wide open throttle, it should go rich. You should always see a 0.8 or better voltage at wide open throttle. It goes into open loop at wide open throttle anyway. And of course, if it's pulling good at top end, you're in good shape. If, however, you have hesitation, maybe you have detonation when you get down on it, or maybe when you floor it, the car actually kind of noses over. You feel like that it's wind blowing in your face, and you see the O2s go lean at wide open throttle. Well, then you may have a fuel pressure problem. Maybe your fuel pressure is dropping off. Again, you could have a pressure regulator concern. And if you have a mass air equipped car, you could definitely have a bad mass air sensor. It's sending a signal that the load is lighter than it really is, and it's forcing the injectors to go lean, causing you to have a high speed drivability problem. Okay, that leads me into the next sensor that I want to do some checking on, and that's the MAP sensor, the manifold absolute pressure. And of course, if you have a mass air sensor car, that would be the barometric pressure sensor. What I want to do is we'll plug in that old Ford tool, hook it to the DVOM, and see what kind of readings we get. Let's turn the key on. Okay, we're getting a reading of 1.61 volts. All right, the way you interpret that is you change that to a frequency by using the first 3 numbers. So it's really 161 hertz. Well, a correct reading for sea level should be 159 hertz. Well, this is a good reading because actually these old testers read a little bit high. I think we had a TSB to warn us about that. And I happen to know that a 161 to a 163 reading is a good reading for near sea level. Now, if we were in Colorado and we were, above 6,000 feet, I would have a reading in the 140s and maybe high 140s. But here near sea level, that's a good reading. Now let me start the engine, and then the intake vacuum will come up. Hopefully it'll be somewhere between 18 and 20 inches of mercury, and we should see that reading drop. The hertz should go down. Let's see if it will. Okay, where you see it drop to maybe 110, 109 hertz, that's a good reading. 105 hertz would be 20 inches of mercury. So I know that this is reading just a little bit high, so that's telling me that the map sensor is working correctly on this car. And again, if you had a mass air car, you wouldn't have a vacuum hose hooked to it, so when you started the engine, you would still have the same reading. Now, what if I was getting a reading of, say, 110, 120, and the engine was turned off? Well, unless I was 2 miles above sea level, which I'm not, I would say, I probably have a bad sensor there. But again, what you would want to do, just to make sure, it has a reference voltage wire. You want to make sure that you see 5 volts on that, and then the other one is signal return, and again you should check to make sure that you are getting continuity to ground on that. If you are, then you probably have a bad sensor. Now unfortunately there's no real good way to test these sensors without this little tool here, and there are some DVOMs that will read frequency, but I find they're not really reliable. When you probe that signal wire, you don't always get a true reading. So it's best to just replace it with a known good sensor and then see if you've taken care of your drivability concern, what have you. At the chalkboard here, let me just summarize. The map sensor and BARO sensor are essentially the same sensor. On a speed density system, you have a vacuum hose hooked to the intake, and on a mass air system, it is just left to atmosphere. A reading of 159 hertz is correct at sea level, give or take a little bit. It will depend on temperature and barometric pressure, of course. At 20 inches of mercury, vacuum on the intake, it should be close to 105 hertz. Again, there's some variables there. And we saw on this car that was pretty close to being correct. All right, before we leave the subject of sensors, there is one more sensor that I want to discuss, and that's the mass air sensor. Now, the mass air sensor is really a kind of neat device, and on cars that have the mass air system, they tend to have very good drivability from idle all the way to top end. They'll get better fuel economy, and they certainly have a closer tolerance on emissions compared to the older systems like speed density. But there is a couple drawbacks to the design. I understand that many of the aftermarket mass air sensors are real touchy when it comes to mounting. If they're mounted a certain way, they'll give a false signal, so that's a concern. On a stock mass air sensor, you have the concern that you can see on this one here, and that is many of them are very restricted. The hole in the sensor tends to be smaller than the diameter of the throttle body on many cars that they're mounted in. Also, you have a couple wires that are exposed in the airstream. You have what they call a cold wire and a hot wire, and you can get those wires can get contaminated and cause it to send a poor signal. But I think generally with stock Fords, that the mass air sensors have been pretty reliable. So let's go to the chalkboard here and explain a little bit how they work. Now, inside the mass air sensor, you have 2 wires, as we mentioned just a second ago. The cold wire is essentially just the temperature sensor. The hot wire is a wire that has been heated electrically inside the module to a much higher temperature than the outside air or the incoming air. And I think I read somewhere that the hot wire is actually heated to 200 degrees Celsius higher than what the incoming air is. And the circuitry is designed to maintain that exact temperature. Now, when airflow starts going across the inside of that sensor, it starts cooling that wire down. Now, as it cools the wire down, it tries to maintain that same temperature. To do that, it has to add more voltage to that wire. So therefore, proportionally, as more air goes through the sensor, the wire cools down and the temperature has to rise up. That rise in temperature is actually the signal voltage that you're getting that's going back to the processor. And that's letting it know, how to change the shot rate of the injectors, what have you. So therefore, unlike the ECT and ACT, the voltage change is proportional with the amount of air going through. So as the air flow increases, the voltage also increases. And as we were just explaining, as the airflow increases, the hot wire cools down, causing the voltage to rise up to maintain that hot wire temperature. And that's essentially how the system works. Now, unfortunately, for us regular people, there's really no good way to verify the calibration of a mass air sensor. We can check to make sure it's actually working. You can go to the signal wire, and with the engine idling, generally speaking, you should see about a 0.8 volt, but it can vary a whole lot. It'll depend on, engine size, engine RPM, how cold it is outside, all that type of thing. But you should see a voltage, maybe close to 1 volt. Then when you rev the engine up, you should see that voltage go up. I think most of the books will say you should see about 2 volts at 60 miles an hour, but certainly if you rev the engine up, you should see that voltage go up. That'll let you know that it's actually operating, but it won't let you know if you're out of range. Unfortunately, about the only way you can really test to see if it's out of range is to replace it with a known good sensor. Now, many mass air sensors tend to fail to the low side. They start giving a lower signal. It makes the processor think that there's less load on the motor. So what you'll get is, hesitation on acceleration. You might get detonation with moderate load, and at wide open throttle, the car may not have good top end performance. Some of them can be so far out of range it'll actually cause a nose start. And if that's the case, you may get a code for it when you do an EEC test. Or if you suspect that it could be a possible nose start problem, you can always just simply unplug it. If you unplug it, the processor will see that as an open circuit. It will go into a limited operating strategy, and it should start the engine. Now, some people will say, well, I'm building a high-performance car, I'm putting big heads on it, a radical cam, I need to have larger injectors. So how do I go about putting larger injectors in and still have the processor be able to read those larger injectors and have good drivability? Well, most of the time when you go to these high-performance parts catalogs, you will find mass air sensors that are calibrated for a particular injector size. And you wonder, well, how does, changing the calibration or changing the mass air sensor let the processor know that you have bigger injectors? Well, let's talk a little bit about how that's done. Now, I've got a drawing on the chalkboard here to try to illustrate how the aftermarket figures out how to recalibrate these mass air sensors. All right, somewhere at Ford, there's a set of charts that the engineers go by. For a particular car application, they have a graph that they can look at. And I'll just say, I'm using some arbitrary numbers here. Maybe the graph says that for a particular mass air sensor, at 20 cubic feet of air per minute going through it at 70 degrees, they want to see 1 volt on the signal wire for a 19-pound injector. Again, I'm just making up these numbers for illustration. Okay, so the aftermarket gets a hold of this and they say, okay, I want to change this calibration to use a, say, 24-pound injector or a 30-pound injector. And we'll just call it injector X. And they know mathematically that the injector they want to calibrate it for has 20% more flow than a 19-pound injector. So what they want to do is to create a signal to go back to the processor to let the processor think that there's a lower load on the engine. So instead of having, say, 1 volt there, they calibrate it to maybe a 0.8 volt.
which is, let's say, 20% less voltage than what the original engineering number is. So when the processor gets that signal, it says, okay, the load is less. I'm going to send out a signal to the injector to shoot for a shorter amount of time. Maybe with the stock calibration, the injector on a certain RPM was shooting at 2 milliseconds. Now it sends back a signal to, let's say, shoot it at 1.6 milliseconds. It's shooting it for a shorter amount of time. So it would normally run leaner, correct? No, because we're running a bigger injector, it's actually the same amount of fuel going to the cylinder. So from idle all the way to top end, now you've got everything kind of even Steven. So you think, well, if you have everything even, then what's the advantage of having a 30-pound injector? Why would that be any different? Well, what you have to figure is that with the 19-pound injector, you only have a certain amount of modifications you can make to the engine, and then you wind up topping out the injector, where in other words the injector winds up running at its max output. Say the injector is almost on 100% of the time, or say 80% of the time, and at top end, you know, maybe the engine originally would turn, say, 5,000 RPM, now it'll turn 6,500 RPM, and suddenly you wind up going lean at the top end. Well, by having a recalibrated mass air sensor with a bigger injector, everything is still even, right on up. But as you get into the very high RPM range, now you have some reserve. Because remember, now the injector is not being opened quite as long as it was when it had the 19-pound injectors. So as you're raising it up, the voltage goes up, and you have a little bit more wiggle room. You have some room to keep that injector open a little bit longer, and now because the injector, of course, is larger, you're getting more fuel, you're going to have better top end. Now this is fine on a normally aspirated motor, but there is limitations to just doing a recalibration setup with a bigger injector. If you start getting into superchargers or turbochargers, this will way overshoot what you can do with just a recalibrated mass air sensor. In those cases, you almost certainly have to have a custom chip. You may have to have some kind of piggyback system that will come in just during boost. You may even have to go to a, say, standalone processor if you have a really radical setup. But for a normally aspirated deal, you're just going with bigger heads, you know, a little bit more cam. This is really kind of the hot setup. Hopefully this video series has given you some confidence on doing an engine swap, and the second half, with all the information about Ford electronics, it's taken some of the mystery out of troubleshooting the fuel injection system. Thank you very much for watching this phase of swapping a 5-liter engine into a Fox platform, and as always, good luck on your project.